reduces a lot. So your basically number of experiment reduces tremendously. Not only he has provided this, not only the contribution of Taguchi is in providing the scheme to reduce the number of experiments tremendously, but also he has given a systematic, very simplified analysis. Plus, one more additional feature is that in all the design of experiments, if you have to optimize this, you have to optimize in two stages. First, conduct the experiment, do the analysis, then you have to follow one of the optimization technique to optimize the things. But the analysis that Taguchi has provided is built into the system and it gives you the optimum result in one go. Then I say quality engineering because this work basically is related with the quality engineering. That before Taguchi, nobody talked about engineering with the quality. The people say quality control, total quality management, total quality control, etc. But he introduced the concept of engineering. I will tell you what later. And that is the topic that we are covering today. So before we go to the topic, let us know who was Genichi Taguchi. So he was born in Japan, 1924. So he was an electrical engineer. So he worked during 1950 to improve Japan's post-World War II telephone. Actually, being an electrical engineer, he was in the telephone communication system. He was employed over there. And he is also known as the father of the Taguchi method and synonymously also known as the robust engineering. Robust methodology, robust engineering, Taguchi's method, quality engineering are all the divisions that basically he is known for. As far as the method is concerned, the Taguchi method emphasizes the attainment of the target value and the elimination of variation. Nowadays, people talk about Six Sigma. Fine, Six Sigma is a good thing. When we say Six Sigma, immediately the thought comes in our mind that it is 3.14 defects per million. So means if I have to achieve the Six Sigma or 8 Sigma or 10 Sigma, means slowly and slowly we need to reduce the variation and finally to the zero. Taguchi says, don't reduce the variation, focus on the target. That if the customer says, I want a dimension of 50 mm, don't ask what tolerance you want. Although customer says, I'm happy with plus minus 2, 48 to 52, I'm happy with that. But okay, your customer is happy with 48 to 52, but you should focus, you should try to provide first time and every time right dimension, that is the target. If you focus on that, then you will eliminate the variation. That is the main focus of his methodology. This method was first applied in 1950. And as the Japanese culture is that they don't publish immediately. So any new thing they get it, they try to reap the benefit for 10, 20 years. And it later basically in 1980, it was introduced in America. Almost 30 years, they did not tell to the people, not published anything. And the Ford Motor Company, they took the lead. They understood that methodology. They took the lead and they applied this concept. It took 10 years to implement in their car models. And this methodology can be applied to product, can be applied to process optimization, product optimization. And as of now, in Ford Motor Company in America, there is a dedicated section of more than 200 employees who are working on the product and process development by using the Taguchi's method. Then coming to the, because I added the word quality engineering, let's see, because most of the people know what quality is. Quickly, I am telling you, there are various definitions provided by the different quality gurus. But this definition was given by Edward Deming. He said the quality is what? Being within the specification. So long as your product meets the specification, it is the quality. He only talks about specification, whether the product functions well, whether the product performs well, whether the product is durable or not. It doesn't talk about anything. So Edward Deming said, if so long as product is within the specification, it is quality. Then Philip Crosby mentioned that so long as the product conform to the requirements, it is quality. So that is another guru. Joseph Juran said, if the product is fit for use, that is the quality. And finally, first time around 1980, the word customer came in this definition. So up to 1980, nobody used the word customer in the definition part. So he said customer satisfaction. If your customer is satisfied, so no matter whether it meets the specification, whether it is conforming to the requirement, fitness for use, I don't care. If customer is happy, I am successful. So Feisenbaum given this definition, focusing on the customer satisfaction. So this is how the quality guru before Taguchi defined the quality. Now question is that suppose I produce a product and I give to you. So you will check everything that okay, specification is okay, requirement is okay, fit for use, performance is there, reliability is there, durability is there, cost is also okay, fine. So you take the product and start using it. After 2 months or 6 months, the product is not performing well. So when your product is not performing well, certainly you feel because at the time of purchasing, they were saying the life of the product is 5 years, and after just 6 months, it is not performing well. So you feel cheated, and when you feel cheated, you just call the dealer. I purchased this product and it's not working. And dealer is very prompt. He says, okay, now sir, please send the product back to us. We will see what the problem is there and we'll fix it. Whatever the problem, we will fix it. So you send the product, they fix the product and send back to you, and it is again functioning very well. You may ask, just as a courtesy, that is any cost involved? Should I pay it? They say no. You need not to pay. We have done it. Now question comes here. All these definitions that has been given by the quality guru are static. Yes, if I am buying, I am checking everything, specification, requirement, fit, etc. But none of the definition is a dynamic definition. So whether I pay or customer pay or dealer pay or the manufacturer pay means some additional cost has been incurred, which ideally it should not be, because when I say the life of the product is 5 years, in 5 years, apart from the regular maintenance, no other cost should be done. So it is a loss to the society, even if the cost is not involved, because I sent the product, they basically fix the problem. Some efforts have been put in to make the product perform well. So Taguchi basically added one more dimension in the quality, that is the time dimension. And what Taguchi says with respect to the quality, he says the loss imparted to the society. Whether I pay or dealer pay or anybody else pay, that is unnecessary money or efforts being consumed. And what he says, time dimension. From the time a product is shipped to the customer till the product dies, means during the entire life cycle of the product. If I say 3 year life is there, so from the time it is shipped to me till 3 years, no additional cost should be there. So the way he looks at the definition, he has provided this definition. He is the first person to articulate that no amount of inspection will ever improve the quality of the product. If you visit any company, You ask, what are you doing with respect to the quality? This is, sir, we have many inspection station. After every process, one inspection station is there. Yeah, fine. So you are inspecting your work. I have done some turning operation. I checked the dimension. But inspection, you are not talking about quality. Inspection is an audit tool. You are making just separating good from the bad or bad from the good. 1,000 products you made, 900 are okay. So inspection is not adding anything quality, but it is a misconception. People say inspection means quality. No, it is not a quality. So these two important things Taguchi has mentioned. With one is the definition, and second is the inspection. So what he said, quality must be engineered in, since it cannot be inspected out. I add it. He said it should be engineered in, it cannot be inspected out. I say it cannot be manufactured and it cannot be inspected out. Manufacturing people, basically whatever the dimension designer gives to me, I try to meet that dimension. So I'm not adding anything to the quality. Means the designer must take care of all the aspects with respect to the quality. So he basically shifted the focus from manufacturing to the design, that all the things must be engineered in right at the design stage. That's why this, when this word engineered in came, the quality engineering branch has come up. In America, there are specialized program, master's program in quality engineering. And since he mentioned engineered in, so he brought the concept of offline, because there are two concepts. One is offline, one is online. Online people are doing way back since ages. Online means manufacturing and onward, taking care of the specification, taking care of the quality during manufacturing, during performance testing, assembly, packing, shipment, installation, everything. So that is the online concept. So Taguchi focus that, okay, whatever you are doing in online, fine, but you need to focus more on the offline. Offline is design, purchasing of the right material. Then manufacturing engineering, where you decide about the process plan, which processes I should use, what are the route sheet, what at what speed, at what speed, at what depth of cut I should do it. And then once they optimize it, they send it to the manufacturing. Okay, now you go for the turning of this particular part, and when you turn, you use these parameters: 300 rpm speed, this much feet, this much whatever, and you do it like that. So it says that offline, when you use the quality in offline, and what you do, you not only improve the quality but reduces the total cost right in the design stage. He classified the quality characteristics also. Basically, although these are the Taguchi's loss functions, Taguchi's loss function, and the concept is like that. Concept is like that. That if you see the first one, if you see the first one, customer says that my target is 50 mm. I'm happy so long as you give 48 and 52. So these are the specification given by the customer. Taguchi says focus on the target. He says that if you are producing at the target, your loss is zero. Any deviation from the target means loss, and that loss is a quadratic loss. Suppose I produce a product and that product is of this specification cross. It is not at the target, but within the specification. Customer is happy. Customer says, fine, it is between 48 and 52, I will buy it. But when customer starts using it, maybe after 1 year, it goes out of the specification because of the wear and tear. Either way, here also, It is possible. It will go out of the specification. But if customer buys a product which is exactly at the target, by the time he uses it because of wear and tear, it will go out of the specification by the time the life is over. So whatever I am saying, the 3 years is the life. So it will take 3 years or more than 3 years to get it out of the system. So that basically is the loss function he has given. And he has given the loss functions. I think more than 1000 loss functions are ready, available in literature. But being a mechanical engineer, I observed that these are the three loss functions which basically takes care of most of the situation. Most of the mechanical engineering related problems are covered in these three loss functions. One is the nominal value is the best. So when your whatever that your research is there, you're talking about two-way dimension, like the example is also mentioned, diameter of the shaft. The loss function is this, and mathematical equation for the quadratic equation. This is a quadratic equation, simple quadratic equation is this.
Yeah. दोनों को भी 100 का डाल दूंगा.
Please mute your mics. Then the second loss function is smaller the better. Many times we come impurity in the drug, surface minimum surface roughness. So we want the lower the better type of situation, and sometimes we get the larger the better. So these are the different loss function depending upon the quality characteristics that we are taking care of. If you are talking about the strength of the structure, 15 Newton per millimeter square, so we think always larger the better. So that's way basically he has given the various loss functions. So whatever I mentioned up to now, if I summarize, that basically represents the philosophy of the Taguchi method. What is the philosophy? I already mentioned quality should be designed, engineered into the product, not inspected into it. So inspection will not bring, he said it should be designed. Second, we talk about quality is best achieved by minimizing the deviation from the target. Try to produce at the target. The more the deviation from the target, more the loss, because it is a quadratic function. The third is the cost of the quality should be measured as a function of deviation from the target system-wide. When I say system-wide, means any additional cost when we are considering from the time the product is shipped to the customer till the product dies. Means during the entire life cycle of the product, we are basically talking about additional cost. So ideally, this additional cost should be zero. Should be zero. So that is basically these three sentences basically tells you the whole story of the philosophy. So this philosophy, you need not to bother about when you're using it. He has given the methodology to implement in a very systematic manner. You just follow the steps, everything will be taken care of. That is the concept of quality Taguchi mentioned. Already I explained in the previous slide. That is actually the traditional concept. We all know, I already explained that if customer is asking for target 50, 48 to 52, so means if your product is between these 48 to 52, your product is pass, otherwise fail. That is the traditional concept. But the Taguchi concept, I already explained, if you are at the target, your loss is zero. Anything goes beyond means your loss is increasing in either direction in a quadratic manner. So that concept he has given, that is the loss function concept he has given, and that is basically represents a paradigm shift, the way in which company measures the goodness of the product. Many times we say good enough. This is okay, good enough. Good enough means chalta hai culture. Chalta hai culture will not work. You have to be specific that if customer says 50, try to produce at 50. Maybe suppose you produce at 49, customer will buy the product, but that may create a problem when customer starts using it till the product dies. So that is the concept of the quality. One is a traditional, one is this. And just an example that was published way back in 1979 in a newspaper in Japan, like Times of India in India. So that is the title of the newspaper is Ashi. So in the Ashi newspaper, this story was reported. What is the story? That there is a one company that is a Sony television. That company is in Japan. They are manufacturing each and every component, every part of the Sony television. And that company basically now has the two assembly unit, one assembly unit in Japan, another assembly unit in America. So the parent company is sending all the component parts, etc., to both the companies. Along with the parts, etc., they are also sending them the operating condition, assembly condition, etc. So both the company, one company in Japan, one in America, both are assembling the parts provided by the parent company. They observed that people in America, they prefer to buy the Sony television assembled in Japan in place of Sony TV assembled in America. So that was a very surprising thing, that same parent company, same component, same operating instruction, but people in America prefer to buy Sony assembled in Japan than Sony assembled in America. So that basically is the story. Identical sets were assembled in Japan and America with the same design, same parts, same process control. American customer preferred TVs assembled in Japan to those assembled in America. Why they were preferring? Because of one characteristic, that is the color density. So they observed that American televisions are color density is not but is worse than the color density of the Sony TV assembled in Japan. Also, that was another observation. None of the set that was assembled in America was out of the specification. Means 100% fine. All the product they produce in America 100% okay. While 0.3% of the set were out of the special. Means Japanese product, Japanese TV was 99.7% fine. Still people preferred that. And the reason was the approach. Reason was the approach because American followed the traditional approach. That customer is asking, suppose 50, the same example, 48 to 52. So they given the instruction, when you are fixing the color density, fix between these two. So they've just assembled it, adjusted between these two. But Japanese were basically focusing on the target. They tried to adjust to the target. So most of the sets that they were producing, that are at the set at the target. So that was the philosophy, the way of application of the thing. Right. Then comes the process. So this quality engineering that Taguchi has mentioned. So his analysis basically involves three steps: system design, parameter design, and the tolerance design. So whether you are going for a product design or a process design, the steps are the same. Steps are the same: system, parameter, and tolerance design. And if somebody says, "What before Taguchi?" I say yes. Before Taguchi, also people were designing the product. People were designing the processes. It's not like that when Taguchi came only then all these things happened. But his main contribution is in the second step. His main contribution is the optimization of the second step. Like if suppose we go for this link product design, the first step is go for the system design. So what is system design in product design? Is visualization or conceptualization of the product. So I think that there is a need of this product, then I visualize it, then I conceptualize it, then I start thinking of the product. And before Taguchi also people did it. People used to do the same way, right? But in the second step, parameter design, people were using the parameter design, but not because they say, okay, this product is there, three component of this product. One component requires drilling, one component requires milling, one component requires turning. So this, they say, okay, this you focus on the specification, do this turning. If it is not working on 300 RPM, work on 400. So they basically randomly doing it and trying to meet the specification rather than focusing on the design. So they were only focus was that we have to meet the specification irrespective of whatever the RPM is there. So that because of that, there was a product to product variation. Some products are being manufactured at 300 RPM, some at 400 RPM, some 350 RPM. So means there was a product to product variation. Taguchi focused on this. He said, no, before sending the material to the manufacturing, in the design section, you do the robust thing for parametric thing. Means find out what is the optimum parameter, what is the optimum speed, feed, depth of cut, etc., etc. So that is the second parameter. That is important. Third is that it is again very common tolerance design, fine tuning of the parameter. Suppose your optimum speed comes 300 RPM, but when you go to the manufacturing, they say, I have the machine which there is no possibility of fixing at 300 RPM. Yes, I can fix at 290, I can fix at 310. So that is the fine tuning of the parameter that is done. So that basically is the tolerance design. As I already focused, the Taguchi's main contribution is the second stage. And this second stage is, because of the second stage, it is known as the robust methodology or robust design. Now, question comes, what is robust? Right? So before coming, what is robust, we should know the objective. What are our objective? Our objective is to improve the quality of the product by minimizing the effect of variation. Because suppose if you go for turning 350 RPM, you go for turning 400 RPM, what is the effect of 350 or 450 on the surface of the material? That basically we want to minimize the effect, because we want first time and every time my product should be the same, exactly same. It's without eliminating the causes. Because you can't, sometimes it's very expensive to control the causes. So that is our basically main objective in robust methodology, is that we want to minimize and tending to zero the variation in the product. And what is the end result? End result is a robust design. What is robust design? A design that has minimum sensitivity to variation in uncontrollable factors. Because speed, feed, depth of cut, etc., you can control. Like in casting, you can control the pouring temperature. You can control the pouring speed, pouring time. You can control it. But can you control the pressure, atmospheric pressure, humidity, temperature? Although you control the temperature, by the time you start pouring into the uh, mold, the temperature basically goes down. So he says, whatever the, if your system, if your design is efficient enough, that has, it should be minimum sensitive to the variation. Means the effect of uncontrollable parameter should be negligible. Controllable parameter you can control, but the effect of uncontrollable parameter should be there. So that is what basically robust design is. Then After knowing all this concept, these are the steps. One by one, if you follow, you need not to bother, but the methodology is there, you will get the right result. So these are the step-by-step methodology. I can say also steps in the Taguchi method, steps in the robust design, steps in the parameter design, all are the same thing. So when you want to do research, when you want to use this technology, this methodology, the very first step is identify the problem. What is my problem? Suppose I say, I want to optimize a turning operation. I want to optimize a casting process. So many welding process, casting process, TIG welding, MIG welding, whatever. My problem, first thing is you need to identify the problem. So why I'm saying identify the problem? Because once you say I am working in a foundry area or a metal casting area, I need to understand, I need to have the entire knowledge of that. If I do not know my specific area, so how I will understand the system. So once you say, I suppose I say I want to optimize the turning of process, fine. Okay, first half part is over. Then it says response characteristic output. I want to optimize a turning operation so that the surface roughness is minimum. So surface roughness becomes your response characteristics. So that is the first step. Second step, and between the first and second step, I would like to say that it comes the critical review of literature in the machining area, in the surface roughness area. So once you understand this thing, then you do conduct brainstorming session. You call the experts or your professors, your colleague who are well known about this area. Ask them, conduct the brainstorming session and find out what are the various factors. Make a list of the factors. Yes, turning also affect so many things. Coolant also affects, vibration affects. So many parameters are there. Make a combined list of the parameters. So once you identify all the factor, whether it is a controllable factor, whether it is an uncontrollable factor, make a list. So once you make a list, then just for sake of clarity, how these factors are related, you develop a cause and effect diagram, fishbone diagram, or some people say Ishikawa diagram. So once you prepare the diagram, the entire things will be visible to you, very clear to you. Then out of all the factor, you identify, classify that out of 20 parameter, 15 parameter are control parameter. Means control parameter means that you can control. Because Taguchi was an electrical engineer, he used the word noise. Noise normally is used in electrical engineering. So then you identify noise parameter. Noise means the parameters that you cannot control. And third is the signal. Signal means the parameter. In every process, you will find at least one parameter. Like in the machining operation, the feed is a signal parameter. Because if I change the speed, it has a direct relation with the surface roughness. Means identify one, at least every process at least one parameter that directly affects your output. So the information of that parameter is also needed. Okay, once you identify all these parameters, then conduct Pareto analysis. Pareto analysis, many people must be knowing that 80-20 rules. What 80-20 rule is there? That most of the time, 80% of the problems can be covered or can be corrected by only 20% of the problems. So out of 20 parameters, suppose there are few parameters only, they basically contribute to more towards the surface roughness or surface finish. The idea here is that if you start thinking, okay, I will not do the Pareto analysis, I will go with the 20 parameters only. So your life will become hell. When you have 20 parameters, so many experiments you have to do. And many of the factors, if you implement them, they will only contribute 0.1%, 0.2%. Don't focus on those small factors that basically affect the output very insignificantly. Focus only on those parameters that has a significant effect on the output. That's why I written the downsize. Then it says select the experiment. Suppose in the machining operation, we selected only three parameters. We know there's three parameters, the significant parameter. Rest are, yes, they affect it, but the effect is not much. Speed, feed, and depth of cut. So when I identified that there are three parameters, then I will identify the range. Okay, in which range? Suppose speed, I say 200 to 500. I will explore the entire range and will try to find out the optimum. Feed, 0.01 millimeter per revolution to 0.03 millimeter per revolution. Depth of cut, 0.005 to 0.01. So like that, we gave basically decide about the range of the factors. Once you are decided, then here comes the standard orthogonal array matrix that is available. You need not, like in design of experiment, you have to design it. Here you need not to design. Standard metrics are available. Taguchi used the terminology as orthogonal array, and this basically is the orthogonal array. If you just see the bottom, these are basically the symbols to describe orthogonal array. If capital L means orthogonal array. You need not to say, if you write capital L, this automatically means orthogonal array. The subscript to this represents total number of experiment you need to conduct. And within the bracket, it is written 2. This represents the number of levels. Suppose I say, I will explore the speed from 200 to 500. I also take the decision. I will only conduct the experiment at 200 at 500. Means my levels are 2. But I always advise all the people that if you are a mechanical engineer doing research in mechanical, never go for 2 level, minimum 3 level. Because if you have 2 level, you will get only 2 results. So when you get 2 data, you have the tendency to join these 2 points by a straight line. So none of the problem in mechanical engineering is directly straight line. So at least you have a 3 points so that you know whether it is a linear relationship or whether it is a second order relationship or a third order relationship, so that you can find out. And K represents the number of parameters, number of factors. Okay. Now the same, suppose you have 5 factors and all at 2 level. You have to conduct how many? 32 experiments you have to conduct. But Taguchi says what? If you see this or particular orthogonal array, now actual orthogonal array. L means orthogonal array. How many experiment? Only 8 experiment. How many factors you can include in this matrix? 7, because there are 7 columns. So up to 7 parameters, you only have to conduct 8 experiment. And if you go for the traditional design of experiment, how many experiment you have to conduct? I think 128. So that basically the beauty of this thing. So that basically the ready-made orthogonal arrays are available. Then he not only orthogonal arrays for at different levels, he has also provided the mixed level. Like say for example, there is one there are many situations when one parameter at 2 level, even if you want that I all parameter I want at 3 level, like pulse on, pulse off, coolant on, coolant off. So there is no in between situation. So you have a situation where one parameter is at 2 level and 7 parameter at 3 level. So traditional methods will not help you. even that can also be accommodated. If, if you see here, say for example here, 3 level 13 parameters, only you have to conduct 27 experiments. If you use the full factorial design, 3 to the power 13 means so many. I can't calculate like that. If you have 4 level 21 parameter, only 64 experiments. And another thing is you need not to worry. These standard tables, standard metrics are available directly. Only your expertise is there that you have to select the right orthogonal array. All right. So once you decide orthogonal array, why we are deciding orthogonal array? Because this is a scheme of experiment. Again, I am showing you that, sorry, I put, clicked on the wrong place. Because this matrix that I was talking, it has 7 columns. 7 column means 7 factors. It has, when I say 8 experiment, means there are 8 rows. Means first experiment as per the first row, second experiment as like that. That basically I wanted to tell you about that. So when we say decide about the orthogonal array, means scheme of experimentation. Means at what setting I will do the first experiment, second, third, etc. So once you decide it, then naturally the next step is conduct the experiments. So you conducted 8 experiments. Suppose you are measuring the surface roughness. You measure the surface roughness, eight samples are there, 8 values you have obtained. So once you have the measurement, then do the analysis. And when we say analysis of the data, and analysis is very simple. Everybody knows, every engineer knows what is ANOVA. You just use the ANOVA and find the effect, main effect, analysis, significant, non-significant parameter, correct? So you do the ANOVA. But once you do the ANOVA, second part is important. First part is okay. Actually, in this, you once you have the measured data, means actually measure the surface roughness. That data normally, in technical term, we use the term raw data. So you, when you have the raw means actual data, you conduct ANOVA. Fine. Second part of the analysis that I told you in the beginning, that this is the methodology, the advantage or beauty of this Taguchi method is that optimization is inbuilt into the analysis, and that is in the second part. What he says, do the signal to noise ratio analysis. Now question comes, when I do the signal to noise ratio analysis, I should have the data. I only have the measured data and I have done the raw data analysis. And means you have to theoretically calculate the signal to noise data to do this analysis. And if I see this ratio, S by N, S signal and noise. Signal is a good thing. Signal means corresponding to my response, my output characteristics. Noise is disturbance. So when I say signal to noise, I need to maximize it, because noise is the bad thing. I want to maximize this ratio. So when this means, if I develop the objective function is maximize S by N. S is the output, N is the disturbance. So that basically subject to the condition. What are my condition? My speed should be 200 to 500. My feed is this much to this much, and depth of cut is this much to this much. So this basically indirectly we can formulate a objective function optimization problem. Objective as a maximize so and so, subject to the condition. So this, and this. Now, question comes, how theoretically we can get the data, because we want to do the analysis. So there are various mathematical equations he has provided depending upon the type of characteristics. Suppose surface roughness, it is smaller the better. So you should know what characteristics I want to optimize. That is smaller the better. Whether larger the better or target the better. Only one thing always remember, that whatever the type of characteristics you have to maximize this ratio. Now question comes, how to get the data. The data you can get depending upon the, first you understand which characteristics you are talking about, then corresponding equation you can use and can find out the data. So once you have this, these are the theoretical data. Normally in Taguchi methodology, we say S and data, S dash and data. One was the raw data, we did the analysis. Now theoretically we are calculating S and data. So once theoretically, because if I had done 8 experiments, I will get 8 theoretical data. I will do the analysis of variance on that also. So that's how basically we optimize it. So once you analyze the result, then you find the optimal setting and then confirm the results. Confirmation means by conducting a repetition or more experiment to confirm or validate your results. So these are the steps that we employ in the Taguchi. That is all about the Taguchi's methodology. Fine. Now I just quickly will give you the one case study that basically is the output of my one of my master's students. So he basically worked on this surface roughness optimization of some casting process. So if I say the first step, identify the problem. But he identified that I have to optimize a vacuum process of the casting. On what characteristics, what should be my output? On surface roughness. Correct? So once you identified that what is your topic, what is your response characteristics, then you have to study all about casting. What are the casting process? What is specialty in vacuum process? What are the parameters? Because you have to see, because many people have worked already on it. Which parameter affects which way, like that. So you study all these things. Once you have a thorough understanding, then you conduct the brainstorming session. So when you conduct the brainstorming session, you call the experts, you discuss with the people, discuss with supervisor, and make a list of the parameters. Identify the list. Means once you identify the list, then you develop a cause and effect diagram. This is how basically the cause and effect diagram has been developed. So he says, my focus is on this process casting quality. I want to improve the quality. And as far as quality is concerned, I am only focusing on surface roughness. Now, the surface roughness of this casting process is affected by the sand I am using, additives I am using, alloy, vacuum, vibration, plastic film. All these basically are the things that affects the surface roughness. Then say for example, within the alloy, when I say alloy, composition of alloy matters. Pouring temperature also matters. Pouring time also matters. When I say sand, what type of sand, whether it is a silica sand or a chromite sand or a zircon sand, whatever. What are the shape of the sand grains? What is the size of the sand grain? Like that. So we make a list of the things and we identified that these are so many factors that affect the quality. I'm not saying which is significant, which is not. Initial is make a complete list of the parameters. So once you make a complete list, then do the Pareto analysis, downsize, means selection out of so many factors which my expert or which through the brainstorming we say which are the significant parameters. And when we studied all this problem, we identified there are the 5 parameters that are we thought that degree of vacuum imposed, because it's a vacuum process, that affects pouring temperature, also affects the sand fineness, means the size of the sand grains also affects, amplitude of vibration also affects, because using the vibration we compact the sand, and time of vibration, the more it is compacted, the better it is, I thought. So we thought that these are the, out of all these parameters, these are the parameters that might be a significant parameters. And we have given the name A, B, C, D, E. And also we decided, because once we identified the parameter, these are the controllable parameters. We thought range, that will go for 200 to 500, 50 to 150, 10 to 60, like that. Also, we decided that we will work on 3 levels, not on 2 levels. So 3 level means we'll explore, we'll do the experiment at all the 3 levels. So that is 2 or 3 decisions we have taken. One is identification of the parameter. Second is the range of the parameter. Third is the levels of the parameters, right? So we identified 5 parameters. Okay. Then we also thought that many times there is a combined effect also. Many parameters individually may affect it, but degree of vacuum imposed and the pouring temperature together may affect the quality. Means we thought that possible that the interaction among the parameter A and B may affect these A and C, B and C. So 5 independent parameter we had, and now when we thought of interaction, 6 parameters we are also adding it. So total number of parameters now becomes 11. 5 plus 6. Fine. So we have 11 parameters. Then we thought, okay, what scheme of experiment we should? Because one decision we have taken level 3. So we need to find out that orthogonal array that takes care of 3 level and can accommodate 11 parameters. And what we decided, these were the standard, the parameter that we kept constant. Okay. And we basically decided the L27. We notice that there is a orthogonal array available that takes care of 3 parameters and 3 levels, and maximum 13 parameters can be accommodated. So we happy because we have only 11. So anything less than 13 can be accommodated here. And how many experiments only we have to conduct? 27 experiments. We also thought we will repeat every experiment 3 times, just to go for the more accurate analysis of our process. So we did 27 experiment, again 27, and again 27. So how many data we obtained? Because 81 castings we prepared, and on all the 81 casting, we measured the surface roughness. Okay. So then standard, conduct the experiment, collect the data analysis, etc. So that was the shape of the casting we have used at that time, and we measured the surface roughness on all the 3 steps. Here. For one casting, we have taken measurement here, measurement here, measurement here, and average value was recorded. These are the data. If you see these 3, first, second, and 3, means 27 experiment. So for first casting, these were the surface roughness. This is the surface roughness. This is surface. So these 3 into 27, this data is a raw data, actual measurement. And if you see the last column, because my characteristic was surface roughness, that is the lower the better. So I use that equation. I theoretically calculated 27 value. These are your SN data. So now I have two set of data. One is raw data, one is the SN data. So once I know I have my data, my analysis is very simple. Just go for the ANOVA and find out the main effect, plot the main effects, right? So this is the main effects of the raw data. When we plotted the raw data and we did the ANOVA, and these were the result. And if you see first factor, the how the things moved, our character is the surface roughness. So at what setting we are getting the lower surface roughness? We go level 1, level 2, level 3. So if I look at this, all these diagrams or all these chart, I will say to get the lower minimum surface roughness, factor A should be at the lowest level, A1 level. Factor B should also be at the lowest level. So A1, B1. Then I say C. C should be at the highest levels, 3, because 1, 2, 3, and surface roughness is minimum, 3. Fourth one should be 2, D2, and fifth one should be. So that is the raw data analysis. Then we did the SN data analysis. And in SN data analysis, when I say factor A, what is the best level? I mentioned to you whether you are going for a lower the better, nominal the best, higher the better, always maximize. So maximum value is coming here, A1, B1, C3, D2, E3. In this, one more important thumb rule I would like to mention. In this particular research, by chance, the raw data analysis and SN data analysis is same. So whether you are saying taking the decision from raw data or SN data, things are same. But there is a possibility that your raw data result and SN data result may be different. But I always say, because you are optimizing it, when your results of raw data and SN data are different, then select only from the SN data, because that will give you the optimum results. So from SN data, if I say what is my optimal parameters, A1, B1, C3, D2, and E3, that basically is my optimum results. Okay, these are the ANOVA. So this, when I basically converting from symbol to the things, so these are the A, B, C, D. So when I say A1, this means degree of vacuum impose should be 200 millimeter mercury. Pouring temperature should be this much. So these are my optimal settings. So once I designed it, now I will pass on this instruction to the manufacturing people. That okay, you conduct all the casting on these parameters, whether you conduct in the morning, you conduct in the afternoon, or at night, in winter or summer, you conduct on that, and you will always get the surface roughness between these two values. That is what Taguchi says. The effect of the uncontrollable parameters are minimized. Right? Then certainly it is basically that whatever the results I am showing you, basically is the limitation, that they are valid within the range. If somebody says you have given these results, I tried on 180 RPM, sorry, 180 degree of vacuum impulse. So no extrapolation or interpolation you need not to do. So that's why limitation of the study, that these results are only okay if you have to, suppose you say 600 vacuum, so you conduct separate experiment, only then my results may not be accurate. My results are accurate within these things. And then we also validated the experiments, and we find it is coming as, because after randomly conducting the experiment, the average actual surface roughness was coming 4.06. But although it is on the hard side, but still within the range. So that is basically how the Taguchi method is applied, and that is the case study. Now I'm just few minutes, some more minutes are available, so you can ask the questions. I'm open to the questions now.
Hello.
Yadvinder.
Sir, it's Anil Jindal here, sir.
Okay.
Ah, yeah. Sir, is it over, sir?
हाँ, मैंने उसका केस स्टडी कर
Okay,
दिया.
okay, sir.
I'm now asking questions.
Yes, participants, if there is any query you want to ask with Pradeep, sir, you are most welcome. You can drop a message in the chat box as well. Sir, somebody is asking, what is the procedure for Innova test?
It's the branch of mathematics. अगर ANOVA पढ़ाने लगूंगा तो मुझे तो
Definitely, sir, definitely.
Actually, ANOVA मैं तुम्हें बता देता हूँ. ANOVA is the analysis of variance. But when we say the title says analysis of variance, ideally there is no analysis of variance. When you go in mathematics, ideally there is no mathematics. We only talk about the mean, sum of squares, and the sum of the main factors, sum of square of the error factors. So there is no variance, but anyhow, it is the name. But what is the objective of ANOVA? By conducting the analysis of variance, we basically find out, suppose in this example that we have taken 5 parameters, and I will share it again. Just hold on. I will share.
Yes, any other query, please?
I'm sharing this ANOVA.
Okay, fine, sir.
Somebody answer. Something I would like to tell. Yes, if you see this analysis of variance, can you see it? Okay. Now, I told you that we have 5 parameters, A, B, C, D, E. We also have that 3 interaction parameter. And when we do the sum of square, because for every factor we calculate the sum of square and degree of freedom. And degree of freedom is what? Because our parameter was 3 level. So level minus 1, 3 level minus 1 is the degree of freedom. And if you come over here, the degree of freedom is 4. Because A is also at 3 level, B is also at 3 level. So 3 minus 1 into 3 minus 1 is 4. So this is how basically we find the degree of freedom. Then we calculate the variance and F ratio. And based upon the tabulated result, we observed all the 5 parameters are the significant parameters. But initially we thought that interaction effect may affect my quality, but my analysis says no, that interaction effect is not affecting anything. The only independent parameters affect. That is how basically The purpose of NOI is to go for the significant testing of the parameters, whether that parameter is significant or not. Okay, that is one thing. Second, we can also find out the contribution of these factors towards my output. Means the second parameter, that is B parameter, is contributing around 62% towards the surface roughness. So that also means the most important parameter is B. And in this case study is the pouring temperature. Means pouring temperature is very sensitive parameter. I need to, if it is at 675 degrees centigrade, I need to control it as far as possible at 6, because any small variation, because contribution is more, so my output will be affected. Say for example, the last one, 3.28, that is the time of vibration. Even if, because time of vibration is 30 seconds, say for example, even if it goes 28 or 35, because contribution is small, so it will not affect much.
Thank you, sir. Thank you for explaining.
Thank you, sir.
So that is the second benefit of the ANOVA is you can find the percent contribution.
Yes, any other query, please, participants?
Your time. Actually, there's a lot of mathematics, lot of concepts were there. So
Yes,
that's why
sir.
I given more time for the queries.
Correct, sir. Thank you, sir. Yes, participants. You can drop a message in the chat box.
Excuse me, sir.
Yes, please.
Sir, how to predict interaction between two variables or more than two variables?
That's you remember the second step between first and second. First step is identify the problem and output. Second step was the brainstorming. I told you between these two steps, the moment I say I want to optimize my casting process, means I need to go for a literature review. I need to have a thorough knowledge of what is the casting process, what are the various type of casting process, what is the research going on. Through the previous research, we understand how the different parameter affects. Based upon that experience, we do it. Suppose that is also possible. Your process is new, no research is available. Then normally we conduct the experiment. So in that case, we are not saying that A and B will affect. So we'll explore all the parameter A, B, A, C, A, D, whatever, all the possible combination. Not only two, maybe three also, A into B into C. So we basically go for the pilot experimentation. Then we'll see which is having the effect or not. Then we decide this.
Thank you, sir. One more small query, sir, question. How to predict non-linear regression analysis? Is it related to linear regression or non-linear regression? How do we predict it, sir?
See, I always say to my researcher students that before jumping to any DOE or any orthogonal, any Taguchi things, first do the pilot study. Pilot study means one factor at a time approach. Correct? Means keep all the parameter at a suppose in this case pouring temperature. Keep all the parameter at constant. Conduct the experiment 650, 675, 700, 750, 800, 900. Do the experiment. Just one factor. See what is the effect of the temperature on the surface roughness. Just effect of one parameter. So when we do this experiment, you will plot the output. And if the output is coming straight line, you say straight line. If output is coming second order, like that.
How to fix other parameters, sir, during this pilot study?
Normally at the center value. Normally it's at the center value.
Thank you, sir. Thank you very much.
Yeah, all the parameter at the same value, center value, whatever the range you are thinking.
Sir, thank you very much, sir. Thank you.
Yes, participants, any other query, please? Sir, I think there is no more query. So on behalf of the organizing team, I would like to thank you for your valuable time and your insights, sharing your experiences with us. So thank you very much, sir.
Yes, thank you. Thank you. Okay.
Thank you very much, sir. Thank you. Sir. Okay, thank you, participants, for being with us. So tomorrow we will again start with at 10 a.m. Thank you very much. See you tomorrow.